Hello everyone, welcome back to another video of structure analysis. In this video we're going to be talking about deflection using energy methods. Now, as we know, calculating deflection for beams, we have different methods: double integration, moment area, tables, conjugated beams. They're very effective in finding deflection for beams that they have simple loadings. You can use them for complex loading, but you will be struggling with the calculation that we have it there. They may take time in order to find specific deflection that you wanted. Now each of them, they have their own advantage and disadvantage. But if you realize that I'm saying beams, I'm not talking about trusses or frames, so I cannot use the above mentioned methods to calculate deflection for trusses or for frames. So in order to find deflection for all of them, we can use energy method, which is a general method for calculating deflection. So it can be beam, truss, or frame. Now the idea of energy methods based on elastic behavior of material. Now we know about stress strain diagram. We assume that the material behave linearly until goes to plastic zone. Now in whole structure analysis, basically the one that limited for undergraduate, we assume that the material behave linearly. So we assume that the material is in elastic zone. We're not going for non-linear behavior or plastic deformation. We are assuming that the material is in elastic zone, so it's elastically behave. Upon removal of the load, the deformation will be recovered. Now the area under the curve here is defined as modulus of resilience. Modulus of resilience is the amount of energy that the material can absorb upon removing of the load. It will bring back the deformation to the original shape. So that the energy that will be absorbed by a material depends on the external forces. You're applying force, the material will deform. This is deformation, we have it here. So when the stress is increasing, stress is in the result of external loads. So the external load will create internal loads. Those internal loads create stresses. The stresses will create deformation. So we can say that the external loads create deformation. So if the deformation is within the elastic zone, the material will be recovered to its original shape. So the energy methods says that the work done by external forces acting on a structure, which we going to assume is UE, is going to be transformed internal work. We already know this one, that any force external will create internal forces, and that's going to make deformation. Or we call energy strain energy. And we assume that those two are equal, because if there is no load, no external, the material is at rest, except its own weight and gravity. We're not going to talk about those. So if there is external load, there will be internal loads. Or we can say that there will be external work and internal work in a manner of with energy, or the external energy, internal energy. Now we assume that those two are equal. Now the idea of energy method is trying to find both of them, both of the external and internal, and from those we can find deflection that we want. It can be used for trusses, for frame, and for beam. So we're going to explain about them. Now when we say internal work here, this internal work can be due to normal force, can be due to shear, which is neglectable, so we're not going to talk about shear. So it's mainly the internal work that we have is due to the normal force and due to moment. So we have two internal force that we're covering it that will affect deflection. Shear also has its own effect on the deflection, but it's very little, so it's neglectable. That's why we're not discussing them in energy method. So we're mainly talking about normal force and the moments. And sometimes also we will discuss them that in a beam, on a frame also sometimes we are, if there is no lateral load, we can neglect normal force. We can explain this one in a practical, in a way that in an example to explain why it's, when it's possible to neglect the normal force, effect of normal force on deflection. So we're going to discuss both of them to see. Now this is the idea when we said it can be used for all the type of structure we have, the beam, truss, and frame, because we have internal forces in each of them, and we can use the idea of external work, internal energy to apply to both of them. Now, as we assume that the external energy is equal to internal energy, so in order to explain the external work, we're going to talk about external work first, external work. Then first we're going to talk about external work for force, which is normal force, we mean here, normal force. Then we're going to explain external work for moment. Now imagine we have a bar, it's at rest, there is no force, so I have no deflection or no deformation, we have it here. When you apply a force, this force will create internal force here, internal force, and this internal force basically will be responsible for deflection. I'm not talking about the internal now. Why? Because my aim is about external. Now this external force, what does it do? It's going to extend or elongate the bar along its direction. So it's going to come down and deformation will increase. Increase the load, deformation will increase. So since we're assuming the material is linear elastic, so it means that this will be the behavior of deformation. Increasing the load will increase the deformation here. So the area under this curve basically will be the external work done by the force, which will be half of the base times height, 1/2 times p times delta. So the external work that will be done by the force, it's equal to half of the load times deflection. Now this is only one load. We can explain the limitations and how we're solving those problems. Now in case if you have moment, now load on the other hand is going to create deflection, elongation here. But if there is moment acting over this bar, the moment is creating rotation. So if there is a moment here, we have it, that moment will create rotation in a way we call it theta. So there will be rotation. The moment basically here responsible for rotation. Now the work will be done by a moment. It's a bit different than the work done by the force. Now why? In the case of moment I have it, when moment is acting along anywhere within the bar, we know that it does not relate to the distance. So when moment is acting here or acting here or acting here, the whole bar basically will be under different deformation. Maybe the angle is going to change according to the location. So that's why we're going to take this theta along the beam in order to find external work, which is going to contain integration through 0 to theta, m d theta which is going to be 1 over 2. It's same manner, 1 over 2 moment times theta. So the external work done by a moment is going to come out similar the way that when it's 0 there is no rotation. When the moment is applying, gradually increasing it, it's going to increase d theta, small theta as we're explaining it, and at the end, if you assume that there is a moment, the external work will be half of the moment, the same way that we assume that it's linearly increasing there. So you realize that finding external work is basically will be half of the p times delta. If this is moment, is going to be the same way, it's going to be the same way, will be half of the moment times theta. Now, if I come to this is external work we talk about. If I come back, now we said that those external work will create internal energy or strain energy within the material. Now, assume that within this, how do you find energy or deformation? We have it inside here. How do you find this deflection? We use stress, because the force is creating stress, and the stress with the modulus of elasticity is giving me strain, and the strain basically is giving me the deformation. That's what we said, that the internal energy that will be stored in the material is due to the external load. So this external load will create a deformation within that we can find it, we call delta here, that is due to the normal force within the element here. By combining those three, we already know this one, NL over AE, it's the deformation of this bar under load N. Now if I combine this one, I already know that, since I know external, by the way, we know that external work is equal to internal energy, yes? So since I'm working with the internal one, I can use external work, which we know that is 1 over 2 p delta, and I know delta from the internal point of view, so I can bring it back here, delta, which we found it to be n, assuming n is equal to p. N should have been f here, there it could be n as well, doesn't matter. So assuming that it's p is equal to n or n is equal to p, because it's the same load acting there, then I can get this equation that internal energy will be, because we know that external energy is equal to internal energy, and we know that external energy basically will be 1 over 2 p, assuming p is equal to n delta, and I know delta from here, so bringing back here will be n square L, the 2 is there, so it will be n square L over 2AE. So it says that the external work will be equal to this value. I mean, I can even say that this is internal, which is equal to the external energy, external work that we have it there. So I can use this idea to solve the problem for deflection. In the same manner, if I go for the bending, now in the bending, since bending it's going over all the beam here, it's not just one value I have it for a moment. This load, when it's acting here, is going to create different moment at different location. It is not as the same as the force here, because within this body, anywhere if you look at it, the internal force is the same. Look, we're assuming that in the beginning we have only one force for the simplicity. Then we're going to explain what's the problem will be happening if you have 2 or more forces. So in the case that we have force here, this force is creating internal force. Any way that you're looking through here, it's the same. But when we have moment, moment depends on the location. So any point that you're taking it here, for example, this segment here, dx, we're taking it, the moment we have it, it has a d theta. So the rotation is different. Take another point, it's going to be different. So when this load acting over this beam, whole the beam will store the energy. Because this force, assuming that this force, I have it here, is going to create moment within all the beam. So it's not just concentrated at one point. This force does not create one moment at this point. It will create it throughout all. Anyway, if you take, there will be a moment. Why? Because whole the beam is working to resist this load we have it here. Now, in order to find the internal energy or strain energy due to bending, due to moment basically, bending, it's due to moment we have it here, we have to take integration over all the beam in order to find. We assume that it's dx, and each dx, summation of all of these dx, which we call integration, just summation of all each those small parts dx, it's going to give us the total energy within the beam that is resisting the load we have it here. Now, how are we going to get this internal energy? Now, again, in mechanics of material courses, we know how to relate the rho, which is the radius of curvature, regarding to the material elasticity and moment of inertia, which we call modulus of rigidity, EI, modulus of elasticity, and moment of inertia of a section. Then with a d theta, then we'll be able to use this procedure. With the moment, sure, there will be a moment as well, because the result of this d theta is because of the moment. So we can use that idea in order to find strain energy, because the moment is creating d theta. So we're relating d theta. The idea is what? To find relation between the moments and d theta. The way that we did it for the deflection here, the relation between the force and the material property, the length we have it here. With the deflection, we're gonna go with the same way, d theta and the moments, material properties. Then we have to go for all lengths of the material, the length of the beam we have it here. Now we cannot just simply multiply it by L. Why? Because the moment is changing depending on the location of the segment that we're taking it. That's why in the case of strain energy due to bending, we have to use integration. Now the same manner, this is what we know from the mechanics of material, that d theta can be related to the moment EI, so m over EI dx. And then if I want to find the total energy, this is just for one element that we take it. For one element, look, this is internal energy, but I cannot say total. Why? Because it is d theta, so I can call this one d internal energy for one element, which is dx. I can say the same way, it's equal to the external work. Then from the external work, we already know what was it, the external work, which was 1 over 2 m theta. Then since I don't have the theta, basically it's why I have theta dx is gonna be there. So there is one moment here, with the moment here will be m squared, but I have dx here, so it's going to be dx here, and there's going to be d theta is going to give me dui. So it is for one element. In order to find for whole the beam, the entire length of the beam, I have to take integration, and that's going to give me the internal energy due to moment. Now why we have to take integration here? Not for the load, because the load, it's going to make internal force within the element, it is constant for a portion of length, but the moment is depending on the x value. That's why I have to take integration throughout the length of the beam in order to get the whole internal energy. And then I can say this is equal to the external work, which is 1 over 2 m theta. And you realize that delta is going for deflection, theta goes for slope. Now whenever we're talking about deflection, we always have slope as well within the topic. So when we're calculating deflection, always will come deflection and slope. So theta here basically is the slope, delta goes for the deflection. Now, let's explain this one in a much easier way to see how we're combining those to find a deflection. Let's assume that we have a beam, cantilever beam, total length is L, and I have a load acting on this end. Now the aim is to calculate delta or deflection under the load, because we know that the external work is equal to 1 over 2 p times delta, and the delta is the distance under the load. Now you realize that we have a problem here, because external work done by a force, it is going to get the deflection under the force. So what if I want to find it here? We can explain this one in a bit. Now let's assume that I'm going to find deflection under the load here, which we call it delta. Now the external work that I have it here will be P. So the external work I have it here, it is known because it's equal to half of the load times delta. Now delta is going to come from the internal, because this load is going to create internal forces. What internal force do I have within this, within here? What internal force do I have it here? Well, we assume that there will be shear, there will be normal force, and there will be moment. Now the normal force, since I don't have any horizontal, will be 0. Shear, we said, is not going to affect in the deflection here for us, so the only one remain will be the moment. So the moment is the internal strain within this beam, because the load I have it here, it creates internal moment. So whenever you take, anywhere that you take, the moment is going to change. Why? Because we said moment depends on x. So we're going to use integration in order to find the internal energy. Well, let's say that this is the external work. We talk about it. So in order to find, we're going to take a section here, and we can find the moment with respect to x. This is a section anyway made, and assume this is x. Now the sign for the moment here, we assume positive sign conversion, because those positive sign conversion is going to give us some result, and the result will have a meaning. So the results will have a meanings according to the positivity and negativity. I don't say that if you assume the other way around is going to be wrong. It's not going to be wrong, but you have to understand how to interpret the results. So if you're going to assume this is the way that we assume for the positive sign conversion, then the result is always going to give you the same meaning. If you assume the other way around, it still will be true, but you have to understand the logics, or you have to use some logical way of thinking to interpret the results. So let's assume that we have a moment in a positive direction, and the moment will be, since they are the same rotation, will be minus px. The moment will be minus px. Now P minus Px is means that it depends on the x. Anywhere that you go, it's not going to be the whole energy, so I have to take integration in order to find. So in order to take integration, we know the internal energy due to the moment is always will be like this, m squared dx over 2ei. Then I know the moment here it's minus px squared. Then taking the integration of this one from 0 to L, it's going to lead us to this value, 1 over 6 p squared L cubed over EI. Now we know that external is equal to internal, and external is 1 over 2 p delta, and internal is equal to this, and I can find the deflection. I have it here. So P will go, this will be P L cube over 3EI, and this is deflection at far end or under the load, simply calculated by strain energy or energy methods. Now you realize that this is only we have one load, and if we want to calculate the external or the deflection under the load, and this is the limitation of energy methods, but luckily there are some theories or some other methods that we can combine it with energy methods to make it general for any purpose of calculation. And there's two methods that we can use it. One is virtual work methods, the other one is Castigliano's theorem. So we're going to explain both of them, how we use the two methods in order to overcome those limitations. Now the limitation that we have it here is explained here, the thing that I told you. So in case if we have more force, it's only one force we explain. What will happen if two force, if I want to calculate different location? If I'm aiming to find deflection at this point, I cannot use these methods. Why? Because this is only says that this delta must be under the load. So if I want to calculate in the midpoint, I cannot use it without knowing virtual work methods or Castigliano's theorem. So we're going to talk about both methods first, virtual work methods, then Castigliano's theorem. Now the principle of virtual work methods, the idea is you assuming that there are some virtual work acting on the body and they create some virtual load within the body. So how I'm going to use this idea to solve the problem? Now, the idea of the principle of the virtual work basically says that the work of external load is equal to work of the internal loads, and this is what we know. We assume that external work was equal to internal energy. Now in this case, for the virtual work, it says that the work of external loads will be equal to the work of internal loads. So what does this mean? Assuming that you have a body, arbitrary body, it doesn't matter the shape of it, it is subjected to different loading. Now this is more than one load, and we are going to find this deformation. Now the deformation is not under any of the loads. This is what we're going to find, this deflection here, this deformation delta in this direction. Now before going to the virtual work methods, now those load we have it here, those load are affecting internally. Yes, if you're taking a distance or something, an element within the body will be deformed by dl, because the load is going to deform the shape. Now this is, we call it real. This is the real structure we have it. Those real structure creating delta L. Delta L is a real deformation due to the real load. So those load we have P1, P2, P3, any type of load will create a real deformation there. Now what we're going to do, in order to find this delta here, this delta, we're going to assume that we have the same structure without the external loads. Without the external loads, we're going to assume one load. So basically, when I say the external loads, I mean the real external loads there. Those are we going to remove them, the real ones. We will assume a load acting on the direction that we want to find delta, because this is what we know from the work, from the energy methods. Now if the load is on the direction of the delta, I can use this idea to find this delta. So applying a virtual load, this load is virtual, and that's what we're going to use 1 kilonewton for the purpose of easy calculation. It will be convenient for our calculation to use 1. It can be kilonewton, it can be kips, any units that you have it. 1 unit load, we will apply it here. Now this load is going to create internal load. This is the same element, Now the U here is the internal forces due to the virtual load. So in the first time, when we had the external loads we have it here, those external loads are going to create deformation on the body. That's going to be dl. Then if I assume that the loads are not there, there is 1 unit load and the direction is on the same direction that I want to find delta due to the energy methods procedure, that the load must be on the direction of the delta or the deflection in order to calculate work there, then this load is going to create internal forces within the body that acting on the length, that the elements that we use it in the first time. Now combining those two, or combining the first equation, that the external work done, the work done by the external forces, it's equal to the work done by the internal forces, is going to get us to somewhere here. Now we can say that the virtual load times the real displacement is equal to the virtual internal forces multiplied by the real displacement. So this way I can calculate any displacement by assuming that one virtual work on the direction of this delta, in order to know that this deformation that I have, this delta, so this is the idea of it. Now this delta has some effects on the actual deformation. That's the idea of virtual work methods. So we assuming that one, it's the unit load on the direction of delta, in order to know that the effect of this direction on the actual deformation that we have it within the body. Now if I was going to find theta, which is the slope, it's basically, we're going to assume this is, in this case, if I'm going to slope, this is going to be a moment, a 1 unit moment. So the moment direction, we're going to assume it here, because for theta we know slope is basically moment is responsible for deflection, the load is responsible. So the load here basically is going to be any direction which is the delta is defining it. The delta is defining the direction of the, and the theta basically is going to define the direction of the moment, which will be clockwise or counterclockwise depending on what we're going to find. Now, then how can I use this one? How can I use this one with the other things that we have it? Now, delta L, let's talk about the first the load, then with the moment. Delta L basically is what? It's deformation due to load. This is only for the load, which is N, normal force. This is delta DL, we call for the real forces. Now real forces, we assume that the real force is creating what? Remember from the beginning we said that it's going to be N L over A E. This was a deformation. This was a deformation due to normal force. The deformation N, which is coming from where? This capital N coming from the real forces. Now let me come back to the slide that we had it. From here, those forces are creating, let's say, N capital, and this N capital is going to give us the delta DL here, DL, which is the deformation for the external force or the internal force we have there. So the delta basically, the DL will be N capital L AE. This N, it's important here to know that this capital N is due to the real load, because this part is because we call the real displacement, this one. But this is in the body, this is within the body. It is not for a specific location, it's within the body we have it. Real displacement due to all the forces, Now, on the other hand, summation of U, it's basically just the normal force. So the normal force, I'll say N, small n, normal force in the body due to the virtual work. It is no displacement, it is just the normal force due to the 1 unit load. So what will happen? It means that if I apply 1 unit load, what will be the internal forces within the body? That's basically N means. N means the normal force due to 1 kilonewton that we're applying it there. We can explain this one on a shape or a truss or a beam. It will be much easier to understand. So the result will be what? The result of combination, this one will be N small, N capital L over AE. Now if you remember, in the previous one was N square. The N square was there. Why? Because the deflection was directly under the load, so we didn't need this virtual load. And at that time we used here P. If you remember, it was P delta. By the way, the 1 over 2 from that side, 1 over 2 from that side is going to cancel each other. So it's P delta, and it was N square, and there was 2 basically here, but the 2 is disappeared here. Why? Because there was 1 over 2 here. Imagining this one before, there was 1 over 2 P delta, and here was N square L over 2 AE. Why? Because the delta was directly under the P. But now this delta is under 1, so the N is not square, will be 2N. N small, which is due to the 1 kilonewton, and N capital is due to the real loads, and that's going to give me, I can find deflection at any location by using this principle. In the same manner, I can use this way, the delta L here basically, because of the due moment, this is going to be the integration that we have it. The integration for M capital here, by the way, is not going to be M square here, It's going to be M capital because it's due to the real one here, M capital, followed dx over EI, and then this is going to be internal moment M small due to the 1 kilonewton, which we have at 1 kilonewton dot meter the moment. And this is going to be integrated over the length of it. So I have M small, M capital dx over EI integrated over the length of the beam. So let's have just to explain in a truss to be much clear what we're talking about. Now, in a truss we don't have moment, so the only form of deformation that they have it here, or the part of energy or internal energy that they have it here, will be due to the normal forces. Now when I say normal force, remember the whole structure working together to resist the load. I have it here. When those two loads applying all the members, we know that from static that I can calculate the internal forces, yes? So those internal forces, what does it mean? Each of them, they have a deformation. Now when we calculate force in this member, I can calculate the deformation inside here, yes? And for this one and the rest of them. So it means that each of the member will absorb some of the energy that will come by those loads. And according to the shape of it, it's going to deform. Now, let's say that we are trying to find the deformation at point B. This is what we want to find. Now, what we have to do first, before going for the virtual work methods, I have to know the deformation, the total amount of deformation throughout the structure. Or by other means, I can calculate N capital, which will be used to find deformation through each of the bars. We have it, N capital, which is the internal force due to the real loads. Now N is going to be different for each bar, yes? So it means that I have to analyze this truss to find internal forces. If, by the way, when I say external, we have those, we know them. If I know them, and it is determinate structure, I can find internal forces. So N capital, it's basically the first part of analysis. We have it here. We can find internal force due to the real load. That's what we call it, N, internal force due to the real load. Then this is I explained there. And N small is due to what? We assume that. So what we assume for the second part of that, we will cancel out those load. We assume that those load will not be there. Why? Because I want to use virtual work. So I'm assuming that those loads are not there. I want to know that if there is 1 kilonewton at this point, 1 kilonewton, at the direction of the deflection that I want to find. Remember, I want to find this deflection, so I have to apply 1 kilonewton at the direction of delta here. Then this 1 kilonewton sure is going to create internal forces within there. So the idea is I want to know that this delta, or the energy that will be perform or create this delta, how much it will be by assuming 1 kilonewton here. So this 1 kilonewton is going to create what? Internal forces again. But this time the internal forces, we will assume them as N small. So each element I will be having N small. So each of them, they will have their own. This will be N1, N2, N3, or basically by N3, N4, So for each bar, I will be having another internal forces, but this internal forces this time is due to the 1 kilonewton. We call those virtual internal forces because they come because of the virtual force that I applied there. Then the total will be what? Summation here. Because if it was 1 bar, this will be the answer. This will be the answer. But since I have multi elements that are resisting the load, that's why the summation comes here. Because remember, the summation means that all the bars are resisting. So there's not one of them responsible for this deflection. Now, all of them together are responsible for the deformation or the deflection of the joint. That's why we have to take summation of n. So this will be I is going to go for bar members. If you go for mathematics way, it's going to be I start from 1 to member. So Ni, N capital I for each member. You're going to calculate this way. On the other hand, so those are explained each of them. What this external I explained for you, the way it's working in small delta and capital L A E, length of the members, cross-sectional area of the members, modulus of elasticity of the member. Because when it comes to deflection, the cross-section area, the modulus of elasticity, the material property, it's going to play a big role there, the length of the member. And those we call N, internal force, internal normal forces in truss member caused by the real loads, and N small, we said internal virtual normal force created by the virtual unit loads. We said that. Then let's have an example to see how we're gonna find deflection. We're using virtual work methods. Now we have a truss, a simple truss here, simple truss. The cross-section area for each member, truss shown is 400 millimeters square. Modulus of elasticity 200 gigapascal. Still, we have it here. Determine the vertical displacement of joint C if a 4 kilonewton force is applied to the truss at C. So the idea for us is to calculate a vertical. It's not going to be like this vertical, but it's going to be, because this is a roller, it's going to move something like this. So most probably the deflected shape will be something like this. It's going to come here, will be something like this. So most probably the deflected shape that we're expecting, it will be this much. This is, we call it a vertical. For the ease of explanation, so I assume that we are going to calculate something, how much this C is going to come down, the deflection in a vertical. It will be something small. I'm exaggerating it for explanation. Now you realize that the deflection is not in the same direction of the load. If it was horizontal, I don't need virtual work method. If it was, by the way, you can use virtual work methods, but if you have delta, if I want to calculate delta, which is horizontal, delta horizontal, I don't need virtual work method. Why? Because I have one force, and the delta is in the direction of the force. I could use the first methods to find delta, but still I still can use virtual work methods to solve the problem. Now, since I know that there will be two analyses, one for the real load, one for the virtual load. So it's going to go in this manner. First, let's say go for the virtual work methods. Now in the virtual work method, what will you do? We say we remove the loads, remove the load. By the way, this is the two reaction we have. It is the same reactions. Those are the reaction we have it here. So what will you do? You're going to apply a unit load in the direction that we want to calculate. We want to find the deflection. Since we want the vertical deflection, we applied 1 kilonewton downward. Now the direction of this one, the direction of the load, it is an assumption. We assume that this deflection will be downward. Joint C after deflection is going to be at the A, somewhere below. Now if you assume upward, You're still right, but the result is going to tell you that if the deflection is upward or downward. So we're going to discuss this one in a bit. So assuming that the force is downward, it means that I am assuming that the deflection is downward. Now how do I know deflection is downward? It doesn't matter, you can assume it in a different direction, but the result is going to tell you that if it is true or not. I mean, true or not, only the direction, the result is still going to be true. The result is going to be true. Now in this methods here, we have to differentiate between the tension and compression. Now, it is recommended to use the sign for them. Now you're going to use joint methods to find the member forces. First find the reactions. Now the reaction will be for this. Like you're assuming two analysis. One, the same truss, there is no the external load, you're removing it, you apply the load in the direction of the delta, and you're going to analyze it. Analyze means that you find the member forces. First, it's symmetry, so we have the two reactions equal. There will be upward. There will be upward. Then we're going to find the internal forces, taking this joint here and the next joint. I'm not going to go for those. You'll be able to find them easily. We call this one virtual forces, N. But remember, this is compression. We needed minus. We have to write it minus. This is tension, because it's come out to be, and we assume this one positive. This has come out to be compression. We're going to assume to be, we're putting minus here because it's going to affect the calculation. So you have to put minus and positive for the compression and positive for the tensions, so that the calculation will end up correct. Now, can I assume them reversely? Yes, but I have to do it the same way for both calculation. Look, you have versatility to do these things, but you have to know what you're doing. So you can assume that tension is negative, compression is positive, but you have to assume the same thing for the other calculation when it comes for the real load. So those are, we call them small n's. Small n's. We have 3 member, 3 small n. We have it here. Then we're going to go for, this time, the real forces, capital N. Now, this time, we have the real force. We don't have the virtual one. And we're just simply analyzing it. This time, we're going to find the reactions. We have it here. Yeah, in the first time, the horizontal reaction is 0, because there is no summation effects is going to be 0. So why? Because we have a hinge here, so AX is 0 in the first time. Just have AY and BY. But here, since the force is horizontal, then we have AX. Then you're going to analyze it in the same manner, joint by joints. You have to take joints methods here. So imagine if you have a long truss, it's going to take time to calculate it, but this is the only way we have it. The only way that we have it to calculate easily the deformation or displacement, deflection in truss will be this method. So you have to analyze it, then you're going to get the capital N's. Those are, we call them real forces. The real internal forces, because they come due to the real force. The real force. Now we're going to use, in those kind of question, it's always recommended to use table to make your calculation easier. The same manner here, look, the compression one is negative, the tensions are positive. The tensions are positive. Why? Because we use the same sign for the previous, for the virtual loads. Then when it comes here, member by member, you have the small n's, the capital N's. You're going to write them down. Then you're going to calculate N, or basically you can go for AL as well. You can add L, you have it L here. So I can just simply calculate even all of them together. N small times N capital over times L over AE. But since AE is constant for all the members, here AE is constant for all the members, that's why we can take it out as a constant common out data, we can use it. But remember, if the areas are not the same, you have to do it for each of them alone. So if the areas are different, you have to add A here, then you have to bring it into the calculation here. Why? Because the easy way to do it is, then you can just take summation here, you will get the summation of them. So here only this part has been calculated, n small n capital, so multiply this by L, it's going to give you this one. Then all of them will be divided by AE. Here why this method used? Because AE is constant for the members, so it's been taken out. Then we used the virtual work equation, which is 1 kilonewton times delta for the point C vertical is equal to the summation of them. Then this is basically the summation here. Since if you're doing with the table, those values, the summation of them, it's going to give you something here. Then you're going to bring it here divided by AE. But remember, this is only when A is equal for all the members. If not, you have to bring A inside here as well, then divided by E, if E is constant. If none of them constant, most probably E will be constant for the members, but sometimes you may have different material within the same truss, so you have to do them over AE for each element, then take the summation. It's going to give you this delta there. In this case, since AE is constant, then I can simply go use, so A since it's 400 for all of them, E is 200 gigapascal, changing the units, because why we used kilonewton in the calculation here, we had kilonewton here, so changing those, basically this is millimeter, change it to meter, and this is 2 kilonewton per meter square. In order to calculate the things, the unit conversion you can do in other ways, doesn't matter. The idea is to calculate the deflection for joint C, which is vertically, and it calculated to be 0.133 millimeter. Now in this manner, any deformation that I have, I can calculate it. Let's say that question asks you calculate the horizontal displacement at joint B. This is a roller, yes? If I'm interested to see how much is this going to go. Now remember, this part of the solution is not going to change. This is not going to change. It's always like this. So the real force is always the same. The only part is going to change is the virtual forces. Why? Because this is true for any kind of deformation. The real force is true for any kind of deformation. So this analysis can be done in the beginning, then according to the deflection, what I want to find, I can do virtual work for that kind of calculation. Since if I want to calculate this horizontal for B, since B is only we have horizontal, we don't have vertical. So if I want to calculate delta B, what I have to do, I have to create in a virtual system, then I will apply, sorry, let's do this somewhere smaller. So assuming that I have the truss, sure there will be the supports at the same way, removing the load, the external load, and applying 1 kilonewton in the direction of 1 kilonewton in the direction of the delta that I want to find. Now this 1 kilonewton is going to create small ends, so I have to analyze this truss for 1 kilonewton here to see what will be the force within those elements. Then I can come back to the same table. This time I'm going to use those n here that I found it for what, not for this one. No, unit load will be here because I want to calculate deflection or displacement at point B. Then I can come back the same. Those going to change. Those will still be the same, or the same. Then I can calculate deflection at joint B. You realize that I can use these methods to find deflection at any point for the truss if I want to. We're going to create another video for beam and frame to discuss them in detail. Thanks for watching.